So, previously we talked about the requirement for electromagnetic theory. We said that there are certain physical phenomenon which electromagnetic theory will better explain and circuit theory will be inadequate for these purposes. So, one can think of electromagnetic theory as some sort of a superset of circuits, okay? And electromagnetic theory is also indispensable if you are going to study microwaves, radar, antennas, fiber optics, optical communications and so on. The primary goal of all these different areas is to somehow harness electromagnetic energy and put that one into a better use. So, electromagnetics in one sense deals with generation, propagation and radiation of electromagnetic energy as well as light. We will see later that light and electromagnetic waves are one and the same, and this union of electromagnetic theory and light was achieved by Maxwell's equations, by Maxwell. We have also studied Coulomb's law, which gives us the force exerted by one charged particle onto another charged particle, and we have seen the form of this force. It requires two parameters to specify. One is its magnitude, which is the amount of the force that is exerted by the particle on another particle, as well as we have to specify the direction along which this force acts. So, force is a quantity which is slightly different or radically different from charge in terms of the fact that force requires both magnitude as well as direction to specify, whereas charge can be specified only by giving its value, number. Okay. So, quantities that require both magnitude as well as direction are called vectors, and we denote a vector in our handwritten note by using a capital letter, okay, to denote a vector, and then we place a small arrow to distinguish that this quantity, the capital letter A with its arrow, is different from just a capital letter. If you do not write an arrow, what it means is that it is a scalar. It can be specified by the number, okay. Whereas if you write an arrow, that becomes a vector. This is the handwritten notation. Sometimes a different notation is used in which you take the capital letter and instead of putting an arrow, you put a over bar. Sometimes you also see people putting an under bar, but that usage is quite rare. In texts and printed materials, you would find vectors denoted by a bold face or a bold print with a capital letter. So, here you can see that this f, vector f, which could represent a force or some other vector quantity, is printed in bold. We also denote unit vectors. We will discuss what unit vectors are later. So, we denote unit vectors by putting a hat or a caret on top of the letter. These letters could be small letters. So, for example, here x hat indicates a unit vector in the direction of x coordinate, n hat indicates a unit vector in the direction of n, or you sometimes find notation by putting up a bold face small letter and then putting a subscript to indicate the direction of the component. So, for example, A being a small letter but bold face indicates that this is a unit vector, and this R subscript to this letter A indicates that this is a unit vector in the direction of R. Similarly, you will also find sometimes Ux written with U standing for unit vector, again a small case letter bold, and X standing for the direction of the vector along which this vector is acting. Now, a vector is defined graphically also by giving 2 points. One is the tail or the origin of the vector, and the other is the end point or the final point of the vector or the arrowhead of the vector. So, this for example is a vector. You have to distinguish between a vector which is directed in this way. Now, if I draw another vector that would be pointing in a different direction, these two vectors will be different from each other. Okay. Now, you also can see that we can perform algebra with these vectors. Before we can go to the algebra, let me just point out that in the graphical representation of a vector, the length of the line stands for the magnitude of the vector. Okay. So, if I have a shorter line with an arrow, that would indicate a smaller magnitude vector, this would indicate a larger magnitude vector in relation to the smaller one. Okay. Now, we want to consider addition, subtraction and other operations on vectors. For now, let us focus only on addition and subtraction. We will come to different operations with vectors later. So, we can add two vectors, something that is familiar to you from your undergraduate studies. So, you have two vectors and how do we add them? So, this is the recipe for adding. Okay. I will not go into the justification of how you obtain this one. I hope that you will be reading up on the reference book or you can recall from your earlier studies. You start with a vector, two vectors that need to be added. So, you have a vector A which is pointing horizontally in this way and has a certain magnitude. Okay. You also have a vector B which is pointing in a direction that is given by this blue line, okay, and it also has a certain magnitude which is given by the length of this line. Now, what is the resultant or what is the sum of these two vectors? Now, before we go to the sum, you have to understand that how did I get this vector B? Okay. Vectors, when you have to perform the sum or the difference of these vectors, have to be defined from a common origin point. Okay. A common origin point for the two vectors A and B is, for example, this tail. Okay. So, tail at this point will be the common point for A as well as B. So, which means that the blue line vector B should actually be defined parallelly over here. Okay. This is the two vectors which are acting, and the vector C, the red colored arrow, is the resultant of A and B. But to calculate the resultant or to calculate the sum of the two vectors, what I have done is to take this vector B and translate it parallelly to get this vector B, which is the same vector, but this vector has its tail at the end point of A. So, this is the first recipe. You can actually translate a vector parallelly in a plane that you want. The two vectors are mathematically equivalent. However, physically they may not be equivalent. For example, I have this object here. Okay. Now, I apply a force along this direction. So, now you can see that this is the starting point of the force and this is the end point of the force. Let us assume that this vector is making contact with this object at this point. So, this is the vector that is acting at this particular point. Now, mathematically you can represent this vector by a line with this as the origin and this as the end point, and that would be a vector that would look like this. Now, you can translate it parallelly. Mathematically, a vector that I am showing here and a vector here both are equivalent. However, physically these two are not at all equivalent. This vector is not at all acting on this object, or you could translate it down, okay, in the same plane. Again, the two vectors are mathematically equivalent, but these two vectors are not physically equivalent. Okay. The reason why I wanted to specify this is because we sometimes get carried away by mathematical operations. Okay. You can actually translate a vector parallelly along a plane, but then you have to always constantly remember that these vectors are not physically equivalent. However, mathematically you can translate them, you can add, you can subtract, and the resultant vector will always be correct. Okay. So, with that aspect in mind, you have a vector B which was originally defined from the common point of the two vectors A and B having been parallelly translated over here. Okay. So, we have parallelly translated the vector B. Now, I want to find the resultant of A and B. This is the second step of the recipe. The first step is to parallelly translate a vector. The second step is to now add the two vectors. How do we add the two vectors? The sum of the two vectors, which in this case sum of A and B, is C, and this is given by a vector which has its origin at the tail of A and at the head of B. So, you can see that the red arrow goes from the tail of A and all the way up to the head of A. Okay. And I have said that you can translate a vector parallelly and they will be mathematically equivalent, and you can see that over here as well. So, I can take the vector A, I can leave the vector B as it is. Now, I can take the vector A and translate it parallelly to get a vector which is this dashed vector. Okay. This is also labeled A because mathematically this vector and this vector are equivalent. So, I have translated this vector parallelly such that the tail of A is at the head of B. Now, I have one tail here and one head here, but you can actually now join the tail of B to tail of A to get the resultant vector A plus B, which is the sum of the two vectors A and B. But please note carefully that this vector is the same as this vector, because you can see that these two vectors are parallel to each other. Okay. This is the law of triangular addition for two vectors, and this is something that you will have to practice a little bit to get familiar with this sum or addition of the two vectors, because we will be looking at not just two vectors, we will be looking to add more than two vectors. Now, how do I add more than two vectors? You do the recipe pairwise, that is, if I have 4 vectors to begin with, call A, B, C and D, first I find the sum of A and B, then I find the resultant of the sum with C, and then I will add the resultant of these 3 vectors to the next vector D, and I can keep doing this one until I get tired, right. So, let us do that one for 3 vectors, and you can actually see that how the process works. So, you have a black line which is representing a vector A, here is its tail, here is its end or the head of the vector A. To this vector I want to add the vector B, okay. B is this blue line vector which is now added so as to get the resultant A plus B. So, this A plus B is the red vector over here, okay. So, I hope this is alright. You have a vector A, you place the tail of the vector B to the head of vector A, and then you draw a line from the tail of A to the head of B, so as to get the resultant A plus B, okay. Once you have the resultant vector A plus B, now I want to add to this A plus B vector a different vector called C, okay. So, now C is a orange vector over here, I am going to add A plus B to C. How do I do that? I have one vector A plus B, if C is not originally at this place, you can translate C somehow. If C was a vector that was defined elsewhere on the plane, you parallelly translate the vector until the C's tail reaches the head of A plus B. Now, you can forget about A and B, and you can simply concentrate on the two vectors A plus B and C. I have A plus B vector and a C vector. You now draw a new line which goes from the tail of A plus B to the head of C, okay. So, this way you can add 3 vectors, and this green line or the green vector is the resultant or the sum of all the 3 vectors, okay. So, I hope this process is convincing. You can show that vector addition is commutative as well as associative by looking at A plus B or B plus A. So, you can show that A plus B will also lead to the same vector C, or B plus A, see the blue line and the dashed black line will also lead to the same vector C, which is just a parallel translated version of this solid red line, okay. So, vector addition is commutative. To show that vector addition is associative, that is whether you start with A plus B plus C, if this is the sum of the vectors that you want, you can first find the resultant of A and B and then find the resultant of A B, that is A plus B and C vector. You can do that one by going first to A and B to get A plus B, to that you add C to get A plus B plus C. Alternatively, you can start with B plus C here, that would give you a vector from the tail of B to the head of C, okay, and from here you can then add a vector A. You will again get back to the same vector. You can try this as an exercise to convince yourself that vector addition is commutative as well as associative. So far we have talked about addition of vectors. We will also need subtraction of vectors. We also need to subtract one vector from another vector. So, how do we do this operation? How do I subtract vector B from A? Remember that subtraction of a vector is equivalent to addition to the vector A, the negative of B, that is A minus B is equivalent of A plus minus B, okay. To get to that one, you need to know what is minus B. What is minus B? Minus B is a vector which has the same magnitude as the vector B, but it will be pointing in the direction opposite to that. It will be pointing exactly opposite to the direction of B and has the same magnitude. Remember, magnitude is a positive quantity, okay. So, vector B, which is defined from this point along this direction, has the same length as the vector minus B, except that vector B is pointing in this direction, whereas vector minus B is pointing exactly in the opposite direction. Now, to add two vectors A and minus B is very simple. You take a vector A, you place the vector minus B, the tail of vector minus B at the head of vector A, and then you draw another line from tail of vector A to head of vector minus B. So, you get A minus B, which is you can call as a different vector D. I hope that you are convinced now that vectors can be added and subtracted. Now, if you are asking or thinking about how do I multiply the two vectors, we will have to wait for that for some time. Okay. We do not really need the multiplication at this point, we will wait for some time before we tackle the subject of multiplication. Okay. So far we have talked about vectors in a very general way. Okay. We drew some lines, then we added lines to another line and we found the resultant line. So, we did all these things. However, this was all the graphical method of doing vector analysis or vector algebra. Okay. You might keep doing graphical methods of vector analysis, but then you will soon tire yourself out if the number of vectors involved is more than 3. Okay. For example, in certain problems you will be seeing that there will be charges which are say 10 or 20 placed around in a plane, and if you want to add all these resultant forces because of all the individual charges, so you will be adding 20 such forces, maybe all of different magnitude and different direction. So, it will become tiresome if you want to carry out the graphical analysis, though graphical analysis helps you in visualizing how the vector would look. Okay. So, we need an algebraic method of handling this. This algebraic method of handling vectors can be accomplished when we introduce a coordinate system. Okay. So, what coordinate systems do is that they help you specify the locations in space by numbers, as well as describe a method in which a vector can be equivalently described by a set of numbers. Now, this is a great advantage. A vector which could be oriented in a random direction in the space is now being described by a set of numbers, and if we also find out how to add or subtract vectors with just these numbers, then we can not only do this as an algebraic exercise, we can also put it onto a computer, okay, input this to a computer, so that the entire thing can be computationally performed. So, you will actually save a lot of time if you are able to associate numbers to vectors, and coordinate systems are the ones which give you those numbers. Now, before we proceed further, I want to clarify one very important aspect. Coordinate systems are independent of vectors, in the sense that if I change the coordinate system, the corresponding vector, the vector will not change. However, the numbers that we associate with the vectors will change. Okay. This soon become apparent to you. We will go with some examples, as you can see. But please keep in mind that coordinate systems and vectors themselves are independent. A vector does not depend on the coordinate systems for its existence. However, the numbers that we attach to the vectors are dependent on the particular coordinate system that I have chosen or you have chosen. Okay. But normally we choose certain standard coordinate systems and work with that, so that there is a minimal amount of confusion.